Okay, so a 200 Newton force acts at an angle of 45 degrees to the x direction on the object with a mass of the 100 kilo. Second force of the 100 Newton acts on the same direction, same object on the angle of 30 degrees to the x direction then. Okay, what is the net force and initial acceleration acting on the object in the x direction, so towards that direction then. Okay, the question is asking you to find what the AX is. Remember that. That's how you need to interpret the question. You're not asking to find the total acceleration, just the acceleration on the x-axis, which is the horizontal axis. Okay, so it's not that complicated. If you ever try to solve a sine and cosine rules, that means you're in the wrong direction. Because once I identify that, oh, this is simply find out what the AX is, you need to find that, oh, what the FX is then. Okay, how do I find the FX? You gotta see this right angle triangle. This is what? F1's X, this F2's X. Can we say the net force on the horizontal axis is the sum of the F1x plus F2x? Okay, then how to find the F1x from the right angle triangle? You know that that's F1 is given as 200 newtons. That's given 100 newtons there. Then using that right angle triangle, F1x must be 200 cos 45. F2x would be the same manner. That would be the 100 times cos 30. And you're almost done. Then therefore the net force on x must be 200 cos 45 plus 100 cos 30. Okay, you may use your calculator to find the exact value times plus that. But for now, I just leave that for some of the values because I want to find that this. I know this is same as the net times MAX here like this, isn't it? By the way, we can't have mx mass on x-axis. It doesn't make sense. We can't have the mass. I can't say, oh, my laptop mass is the 100 kilo on the x-axis. It doesn't really make sense because this is not a vector. This is a scalar. This is something we're giving the terms. So we don't have that. And this means that net mass of this is given as 100 kilo, 100 times AX value 2. Therefore, AX would be 200 cos 45 plus 100 cos 30 divided by 100. Now, the reason why I'm leaving that in the exact value is I want to get this, I want to minimize any significant error. Okay, it's a very important process even here. So now, time to use your calculator once you do that, okay? So 200 times cos 45 plus that 200 times cos 30. That divided by 100, easy, you get 2.28 meter per second, given that the direction here to the right. Okay, this is the net acceleration, okay, applied onto the right, but the question also asks you to find the net forces applied in here too. So let's move on to the part B, which will find the net force. Now, F on Y can be found as all the force components, so F1y plus F2y. In the same manner, that would be 200 sine 45 plus 100 sine 45 like this. This time, let's find this on the value of this. So 200 times sine 45 plus that 200 sine 45, you would get 212.132 newtons up. Finding the some value of the fx, this means that we get the 200 cos 45 plus that 100 sine 30, you would get 191.421 newtons right. From here, I can redraw the force diagram. That is this 191.421 newton. This is what? Net force on x. Okay, and net force of the y, that's a 212.132 newtons. And just simply using the head to tail, the vector sum. Adding these two vectors, you get the vector of the force here like this. this is then equals to, how do we use it? We're not adding the values, we're using the Pythagoras to find the magnitude. So to find the magnitude, that's that square plus 212.132 square. Square root of that, you get 285.73. Now, let's fix that into given a sig fix. We have given, I don't like it, but let's follow that. We have given one sig fig from the question. Means that you need to fix your answer to one sig fig. This is 300 newtons in one sig fig then. Okay, make sure you show them some exact values and then matching that to the sig figs given. All right, theta. How to find the theta value? It can be found from 10 inverse of that, 212.132. The opposite of the adjacent, 191.421, like this. So 212.132 divided by 191.421. And 10 inverse of that, you get 47.93 degrees. So this is what? Approximately 50 degrees in one sig fix again too. So the final answer is the net force is 300 newtons at the 50 degrees above the x-axis or above the horizontal. This is how you finalize your answer then. I know, like, by looking at the working out in here, it looks really complicated. You'll be like, oh wow, so many like sine and cosine, but if you just go step by step, or like some guidelines given, I provided you last time too. Did I give you some kind of template last time? I remember I gave you the template to solve this kind of questions or like in net forces too. That's it. Try to follow that. Okay, it's the same method, universal for year 11 and 12. You use the same method to solve the questions like this all the times. Any questions about Newton's second law up to here? Again, don't just limit yourself and think your thought about the Newton's second law, that is F equals to ma. It's actually more than that. It's more than that. So if you ever taught like in schools that F equals ma, that's a Newton's second law, then you only learned half or maybe a quarter of the Newton's second law. This is the true meaning of the Newton's second law, the net force values. All right, again, remember about this is all about change in motions then. All right, finally, let's move on to Newton's third law. The last law about the Newton's motions, but I hope you understand that it is basically talking about the same motion changes too. So, what is Newton's third law? It's simply also described it as, like it's given it here. If an object A exerted a force on the object B, the object B must exert a force of equal magnitude in the opposite direction and back on the object A. Okay? So, in short, this is known as action and reaction force. Action and the reaction force is simply what we describe that as the Newton's third law. So, for example, you're hammering the nail. So you're exerting force from the hammer to the nail. So what happened is the force that the nail exerted on the hammer, but there will be equal amount of force exerted back to your tooth. Now, think about it here. You may be questioning that then, why did only the nails moving downward, not the hammer? If they applied same amount of force, this is the trick. If they apply the same amount of force in the opposite direction, have a think about it here, what that means here. I gave you a hint that what I mean by same amount of force, but in a case of the mass is on that too. Do you remember the example that I gave you in the beginning of the class today? We have a 5 kilo and 10 kilo, 10 and the 5 kilo, push it with the same amount of force. Okay, push with the same amount of force on the different masses. Matthew, what do you expect if I exerting 10 newtons on both? It will be easier for the 5 kilo to what?
To
move. Just move. Tell me more about the difference in the motions then.
It will be easier to move the 5 kilo object in the direction where you're pushing it.
What do you mean by easier? Can you describe what do you mean by like easier? You're right, but what do you mean by easier?
Like you need like less force to.
Do we need less force? I'm giving you the same force there. See, this is what I mean. Like you're kind of trapped. You're kind of like thinking about it inside it. The question was quite simple. I push the 5 kilo and 10 kilo with the same amount of force, 10 newtons there. Then I'm expecting that we're moving in 2 meters per second squared. Then we're 1 meters per second squared. Okay. What you just need to do is you just need to interpret what that meant in here. What do you mean by 2 meters per second squared, or the acceleration? That means it's experiencing this much of the change in velocity. So this is what I mean by it's moving easier. But there's no, I avoided to use the word easy or hard because it's kind of more subjective. Okay, I'm looking for some more objective terms to describing the motion here. Does it make sense, Matthew? Okay, so which means that the 5 kilo will move faster in the shorter period of time, will move further, which is kind of obvious if you're thinking about 5 kilo and 10 kilo push the same amount of force. 5 kilo will be kind of flying away, 10 kilo will be kind of moving like slower. Okay, this is the trick of the Newton's third law. Students are thinking about, okay, they get the same amount of force. That means that they must have the same movement. No. I've been emphasizing this so many times. Getting the same force doesn't mean that you get the same movement change. It all depends on the masses you're carrying. Have a think about the mass of the hammer to the nail. Yes, nails are much lighter than the hammer. Which means, even though the hammer and the nail experience the same amount of force in a different opposite direction, because the nail is lighter, say nail would be like 10 grams or something, hammer would be like, say, I don't know, 3 kilo, maybe something like that. You're basically exerting the same amount of force on 3 kilo and the 10 grams, then I'm expecting that they will experiencing these different change in motion. Make sense to you, Damien? Okay, 10 grams of nail will experience more of the acceleration than 3 kilo the hammer. I'm giving the same situation as this. If I push that 3 kilo, what about thinking about this 3 kilo and 10 gram with the same amount of force exerted in the opposite direction? Okay, what do you expect? 3 kilo and 10 gram with the same amount of 10 newtons. Just thinking about the motions in that too. 3 kilos is heavier, much heavier than the 10 grams, which means it will move shorter distance. Okay, you actually don't feel that much of force because of the mass too. Acceleration wise, you don't really see that kind of reaction force or the amount of the acceleration kind of exerted. What about this one? This will fly away. Okay, this is a trick of the Newton's third law. Remember this. Remember that this is something that's very important, especially when you're learning about Newton's law in later on, Newton's gravitation law in the module 5 later on. You'll be getting a question like, hey, we are getting some forces now. You're on the earth. You're on the earth. You're now exerting some force due to the gravity, mg. Okay, you also get some force of the normal reaction force. This is the example of the action and the reaction force. Okay, but why is it you only moving, not the earth? It's all because of the mass difference between you and the earth as well too. Which means even though I jump and stomp here, okay, I'm applying the force, I can feel more force from my feet or the foot because of I'm lighter than the earth. Earth is not really feeling that much of the force or changing the motions anymore too. So there was this kind of interesting experiment that down in China, 10,000 people jump at the same time, so it kind of pushed the earth down there. Mathematically, scientifically, that's absurd. Okay, they actually kind of some social experiments doing that. It's a good thought. Think about maybe if we have an exciting great amount of force so you can move the earth with rotational speed. Yeah, but it doesn't happen. But does it make sense to you all too? This, up to here, action and reaction is something you learned in year 10. I'm adding the extra but there's something the extension of that. Remember that the same amount of force in the opposite direction with the different masses will have the different acceleration. Remember that pushing that 10 kilo and 5 kilo with the same amount of force, obviously they were moving in a different acceleration. I'm just simply talking about that in here. Okay, and this is the reason why when you're kicking a ball, playing soccer or playing rugby, okay, you're applying the force to the ball, okay, and the ball's flying off because balls are generally lighter than your body mass. The balls are lighter than your body, means that you can feel that sensation of kicking the ball from the reaction force from the ball too, but not as much. It's not enough to push your feet back. Does it make sense to all too? Okay, a ball is receiving that much of force due to the smaller mass of the ball. It's flying off. It can be flying off too. This is the true meaning of the action and reaction force. Not only just is opposite, same amount, but you need to understand what I mean by same amount in the different masses. This is why you're able to hammer that, because people are asking me, and the students are asking me, is that means like when you're hammering that, it's kind of bouncing back all the time because you get the reaction force? You do. You can feel that some some kind of some vibration. That's due to that of the reaction force. But that vibration doesn't mean that you're this kind of bouncing off to the nails. Does it make sense to all? This is why we are able to hammer the nail. So we can just put the nails into the surface. So, this is what I'm about page 47A. And A, as the hammer gently taps the nail, both hammers and nail experience small forces. B, when the hammer hits the nail harder, both hammer and the nail experience larger forces. In both cases, these forces can be designated by F by the hammer on the nail or F by nail on the hammer. So these two are the same, but you get the different amount of forces applied into. So let's have a think about page 48 in class exercise 2.3. Can you identify, okay, let's do that together too. Okay, let's identify what would be the action and the reaction forces applied to each other. So I give the example, you kick the ball, so you're the one applying the action force. You kick the ball, so the ball, the force on the ball, exerted force, in this case, this is your action force. That means that there will be a ball is giving you that reaction force to you. But have a think about it here again too. Why isn't your foot going backwards if you receive that reaction force? Okay, why is there only the ball is moving forward? It all depends on the mass difference between ball to your foot or to your leg. All right. Second, a bus. Force that bus exerted on the car and the force that. So we have these force that car exerted on the bus pushing forward. I'll call this the action force there. Then bus we exerted force backward. There is a reaction force. Let me have a think about this situation here. We don't want to have that, but imagine that if a small car crashes on the big bus, which car would have the more damage? Small car. Why would the small car have more damage than bus? Because due to that mass difference again too. Does it make sense? Even though you hit that with the same amount of force, the bus is exerting the small amount of, receiving a small amount of acceleration. Therefore, I'm receiving a small amount of the damage than the small car. Does it make sense? Okay. Next one. Gravitational force exerted on the brick is the action force. Action force. And the gravitational force that bricks exerted on the earth, that's known as a reaction force then. You okay, Matthew? Okay? Andy? You alright? Okay? So the true meaning of the action and reaction force, please remember that. Later on, you're going to learn something known as the apparent weight. Apparent weight is like the real weight. Like you if you go downstairs, like downhills, uphills, you feel like you're quite heavy. You feel bodies get heavier or lighter. Then you probably have experience like a flight taking off. Your body feels heavier. You can feel like more pressure, so your body weight can feel like you get more body weight. Okay, when you're landing, you feel like you're flying off. Okay, so you can feel more lighter too. We call that situation the apparent weight. Okay, it's not the real mass you're changing, it's the amount of force you're experiencing in that situations too. I'll probably use that to explain you some elevator questions later on too. This is why when you're going up in the elevator, you feel heavier. When you're going down, you feel like you're lighter. So it doesn't mean like you're losing your weight. It's simply because of the interaction between the forces applied on you. And that makes you feel lighter and heavier. We call that apparent weight. Does it make sense? Okay. All right. So multiple bodies, we talked about there's some tension force applied, so we can talk about this too. I mean, it's too easy for now. Let's think about some of the forces. At page 50, please. This is the one that bothers you a lot from now on. Remember that we are having the action and reaction force. We have the same amount of force applied, but due to the different masses, they will have a different acceleration applied on it. Remember this concept. So the diagram shows the two blocks A and B contact on the smooth surface. A 70 Newton force acts on the block J, and the surface can be considered to frictionless. So we don't really consider about any the friction force in this case. We just ignore that too. So acceleration of the system. Let's think about how to find the acceleration system. So that's A of the system. It's considered to be A of the net acceleration applied on the system there. Let us understand what I mean by system here. You have a system. I'll call this a kind of system here. We have the block J and K's kind of combined together. So the total mass of that system is 6 plus 8, isn't it? Giving you that 14 kg is the total mass of that. Okay, now what is the net force applied? If we don't have any frictional force there, the only force applied on this system is 17 newtons forward. Yes, we're ignoring all the vertical forces because they're not really applicable. They're not moving because we are just horizontally pushing it. Does it make sense? Now, what we learned from the Newton's second law is the net force is equals to the net ma, isn't it? This is the same as net m times net acceleration here like this. Okay, now this is a situation that we can use net amount of the sum of the other masses, which is 14 kilo. That means that the net acceleration can be found from the force divided by the net mass, that is 70 divided by net mass 14, giving you what? 5.0 meters per second forward. All right. B, the acceleration of each object then. Okay, let's think about it in here then. This is the acceleration. We are pushing that. Do you remember that? Even though we are applying the same force, same amount of force on the different masses, creating that the different acceleration. If you're not too sure about this concept, please remember the going back to the 10 kilo and 5 kilos with pushing the same forces. They will have having a different like a motions experience. That's what I'm talking about in here. Okay, so now you apply that acceleration of the net force of 17 newtons. So both of those are receiving the 17 newtons there. Okay, now one is getting the 6 kilo and the 8 kilo. Okay. Everyone good at this stage? Now, assume that this is in a system. This is in a system that's moving it along with the intact. So if you think, you have to imagine this. When I push the J, J will push a K, so they will moving in a one system as you go. So we get intact all the times. That means that this is not really related to this concept then. Both J and K will move in the same direction with the same acceleration, isn't it? when I push the J, have a think about here. This is why you have to use your imagination here. When I push the J and K will be intact, means that they will move in the same system. They're moving along with the same acceleration. They're moving together. Okay, there's a different situation that I'm pushing J and K separately. I'm put the J and K together, push them. So it means that the acceleration applied on the J would be the same as acceleration applied onto the K. That is the net acceleration, 5.0 meters per second squared forward. David, you okay? Sure? Are you sure?
Yeah.
Okay, I'll ask. Because we're going to use that again and again and again. Have a think about the system. Have a imagine. This is why you need to use imagination to understand the physics sometimes too. Because I can't show every single situation in here. I move the J and K is moving in the same acceleration because they're intact, they're moving in the same distance. Yep. Now, then, interestingly, this means that the net force on each object will be different though. Why? The force of the J is founded by mass of the J times acceleration of the J, isn't it? Now, what is the mass of the J? The J box J is 6 kilo. What was the acceleration on the applied on the J? It was a 5, giving you 30 newtons. What was the force applied onto the K then? The force K is founded by mk times the acceleration of the K. That is 8 times 5, giving you 40 newtons there. But, guys, have a think about here. If I add this up, I get the net force, which is 70 Newton. Did I get the 70 newtons? Yeah, obviously I got the 70 newtons. This is net force applied in here too. Which means that if you were looking for the individual forces applied on both the J and K, when they're intact, they will have some of those forces will give you the actual net force value too. Okay, I've got really like a slowly on the step by step because we're going to do lots of the questions related to this. First, think about like the situation that you're pushing that box, they're moving in the same speed, same acceleration, moving in the same distance. Means that indicating that they get the same acceleration amount. Each of the box, because of their mass is different, mass are different, means that they will experience that different amount of forces due to the acceleration then. Does it make sense? Okay. Now D. Then the value of the action-reaction force pair at each constant surface. What would be the action force? Let's identify the action force. Okay, David? Be early. Okay. All right. What would be the action force in that system? Pushing with the 17 newtons is the first. Okay. J and K. So, specifically which one? Is it J pushing K or K pushing J? Okay, J. The force from the J exerted to the box K. Then what would be the reaction force of it? What would be the opposite force? The force of the K exerted to the J. What I mean is the J will push this and the K will push this back. This is the action and reaction pair given there too. Now what would be the amount of the force from J the pushing the K? Any ideas? The force J exerted to the K would it be? Because think about it here. J on the side of the back this side of the J, it got pushed with the 17 newtons. It got pushed at 17 newtons. Okay, means that it will kind of push with 7 newtons and exerted the force of 30 newtons. So this will be 30 newtons forwards. There's the amount of force it's applying to. Okay, J is pushing down the 30 newtons, but at the same time there'll be 30 newtons backwards. Pushed back by the box K to J. I'm just following that, what we learned about action and reaction force, that you have a same amount but the opposite direction. But have a think about it in terms of motion that Yes, 30 Newton forward for the FJ would be a kind of big deal because of the when you're 6 kilo. But 30 Newton for the box K would be 8 kilo. It will not be the big deal as much as not as much as the box J, due to that the heavier mass of that. Okay, it's getting slightly getting confused about action and reaction. Don't just think the action and reaction is the same amount in the opposite direction. It's actually more than that, especially when you're dealing with the pulley questions later on. Again, it's getting more complicated. So it's important to understand first the acceleration of the system. Imagine that you're pushing that, moving it along, get the net acceleration, we get the separator forces from it too. Now, could you try the next question then, 2.4, on question 1, please. Okay, so you have box J, K, L this time, pushing it to the left. Okay, pushing it to the left. So have to imagine that, oh, as you push from this side for the L, you're pushing everything. So they are moving together in a one system. because they're intact, they're coming along with all systems. So A is asking you the acceleration of the system. The way we can find the net acceleration or the acceleration system is by net force applied divided by the net mass. That is, we have the 75 Newton is the net force applied in here because it's smooth horizontal surface. Again, that means there's no friction force applied. Divided by 3 plus 5 plus 2. This is giving you the 7.5 meters per second to the left. This is all moving into 7.5 meters per second. Okay, means all that is moving the same acceleration. B, the acceleration of each object. So it doesn't matter for this in here because they are moving in the same system now. So all that would be 7.5 meters per second to the left. Would it be the same acceleration on L, acceleration to K, acceleration J as well too. Okay, before I move on to C, do you understand why am I writing this? I mean, error. Andy, everyone good? Okay. Then I can move on to C. The net force on each of that, then F of the J can be found by mj times aj. That is, J mass is 3, box J is 3 times 7.5, which will give you 22.5 Newton to the left. F on the K would be mk times A of the K. That is 3 times, the 5 times 7.5 there again too. This gives you 37.5 Newton to the left. And you also get the F on the L. That would be m of the K, L times the acceleration L. That is 2 times 7.5 there again. Then you get 15 Newton. 15 Newton left. Make sense up to here? So this is the individual forces applied onto each of the boxes. Again, because they have a fixed acceleration and a fixed mass, it's easy to find the forces applied. Now D. What are the values of the action-reaction force pairs at each constant surface too? So we would have first the force on L that applied onto the K. Okay. Now have a think about it in here. L is pushed with the force of that, and you may think like this is the same as 15 Newton. So the way we can think about the F on L to the K is, yeah, we have pushed with the 75 Newtons, but this L carries that. So you can think that in here. It'll be the same as net force minus force on the L applied. Because we push with the 75 Newtons, the box L itself carries that force of the 15 Newtons there. So it'll be 70, the net force value we get 75. Okay, and that means that, or you may think like here, this F on K, F the net force, sorry, the force of L that applied to K. Have a think about here. It's a force required to move the box L, sorry, J and K by pushing box L. Okay, so which means when I push the L, I'm also pushing the K and J in the same time. So amount of force required to push K and J is a required amount of force that they're exerting from the box J as well too. What that means is there's a force required to move box J and K. That's a force of the J plus force of the K, then applied in all together. This is amount of force need to be applied onto J so they can move that. Means we have a 37.5 plus that 22.5. Sorry, the 22 point box J to 5 and 37.5. K, L to the K. No, hang on. 15 plus that. Giving you out. Okay, L to the K. Oh, sorry, my bad. Okay, let's write it like here. I give you simple terms. When we need to identify the force L to the K, just think that as a sum of the force L plus sum of the force L plus force K. This is the easiest way to think about it in here. Means that it's applying the force from the L, that is 15, plus that K, that's apply the force of K, that 37.5. This will be giving you that 52.5 newtons to the left. Is the amount of force from L to the K. So that's basically sum of the force from the L and sum of the force of the K. This is an easy way to think about the force then. Because it's simply, we apply the force from the L that push the K as well too. Then the force of the K to L, the reaction force from the box K to the L would be opposite direction with the same amount. So 55.2 Newton to the right in this case. So what about force from the K to J? There will be two forces applied into. Okay, this is same as the force of the K now. As we're K's pushing the J, means that J needs to require to have this amount of force, 22.5. Slightly different in here, I know, because we're using that. So this means the K is now pushing the J, so we're exerting the 22.5 Newton to the left, the remainder forces. Then F of the J to K would be 22.5 Newton to the right. Gives you as this. Okay, this is something that's really tricky to think about, especially the action forces too. So way you can think about for the L's perspective is, I need to push the box L so that it's able to push out the box K and J all together. That means the total amount of force required to push L to K, applied to that is 52.5 newtons to the left. Okay, let's do that some similar questions with it. 2.24 question 2, something that very similar. The JKL again. Next one. We have the JKL again, we're pushing that, so let's find it a system. Acceleration, A system, A. The A of the system, which is same as the net acceleration found by force, net force divided by the mass of the net mass given. That is 54 divided by adding all the masses that you have, 4 plus 6 plus 8. Then you get 3 meters per second squared to the right in this case, okay? Which means all that box is now pushed with the 3 meters per second to the right, and means that we can find acceleration to each object. A of the J is equals to A of the K, that's A of the L, that'll be 3 meters per second squared to the right as well too. Easy, up to here. C, the net force on each object, so the force on the J is now receiving the acceleration of the 3 meters per second on the mass of that, so it'll be 4 times 3, giving you 12 Newton to the right. The force on the K would be 6 times 3, giving you 18 Newton to the right. Lastly, force on the L would be the 8 times 3, giving you 24 Newton to the right as well too. So these are the amount of forces applied on each, the net force applied on that. Remember that this is talking about net forces. These are the net force on the J. So what that means is, let's draw the picture of the J. Okay, I think that's giving you a better idea here. We have a J, the box J. Okay, now this has a net force moving into this direction of the 12 Newton. Does it make sense though? Okay, that means that it has a 2 force component. First, it's get pushed with the 54 newtons on this side of here. All right, okay, but still getting the 12 newtons there. So we are able to find that the opposite force applied to the J, probably the reaction force from that the box K and L, by 54 minus 12, giving you the 32 newtons backward then. How about solving the questions like this? I think this would be easier rather than giving you some formulas there. So let's think about individual blocks in terms of the net force. This is a net force on the J, isn't it? Remember what about net force? We're adding all the force components inside that too. The J's components, the net force in J is given at 12 newtons to the right. It's now pushed with the 54 newtons, which means that it will have a 32 newtons going backwards. It's a 32, sorry, the 42, I should say. 42 newtons backwards. So this means that 42 newtons must be the reaction force from box K to J. So the force K to J is now given as 42 newtons to the left. The force J to K would be 42 newtons to the right then. I mean, according to Newton's third law. Okay, let's solve the questions in this method. This is actually easier and giving us a better picture using the Newton's second law again too. Shall we do the same thing for the box K then? Box K. What about box K now? It has the net force that's moving, it's founded here, 18 newtons to the right. This is the net force value. Alright, then we had a force that is pushing by the 42 newtons to the right from that J to K. So it has a 42 newtons pushing it right too. Does it make sense? Okay. Now, if the net force is 18 newtons to the right, then what would be the opposite force? That would be going the opposite direction like this, and 42 minus 18, which is giving you the 24 newtons. Is the reaction force, kind of opposite force applying onto the K. As we found the net force value. Then this means that F on J, sorry, the last box L to K is 24 newton to the left. Force on K on L must be then same opposite direction with the same amount to the right. This is the final answer then. It's uneasy to think, but if you just apply some net, if you understand what you mean the net force in here, it could be doable. I don't expect you to do like every single question today. This is why I'm giving you like a bit of time to understand and to digest it. But let's try it again. Next one. What about in the situation of this? Page 54, question 3. This time they're not in contact, they're intact, but they're in the strings between them. That means there will be a tension force we exerted. Okay, I'll give you about 5 minutes to think about this, because we can do I'm sure you can do a 1, 2, 3, just A. Okay, give it a go for this type of question then. Have a think about the individual, the small systems. So, hint, what the template is, consider the net system, okay, to figure out the net force. What's the sound? And the net acceleration. So net A or A of the system. That's what you're asking in the question 1 here. Okay, 2. Consider the individual acceleration is the same as the net acceleration. As they're moving in the same system, they're moving along with the same system. 3, find the net force of individuals using that equals to ma. Okay, and therefore find the consider individuals system or the situation to figure out the force components. So this is a template. Write it down. This will be the template that you can use from the question from now on. I will use the same method to solve the question as you go. Okay? It doesn't matter you get the horizontal pulley or some other questions, you can just apply this method too. So I proved that what I mean in here. So let's consider first, consider the net system to figure out the net force and the net acceleration. So what I mean is you have 15 and 30 kilos kind of attached in the strings. So So to find that, the net acceleration can be found from net force applied divided by the net mass that is given in here. This is what? We are given that 225 Newton is applied, which is considered to be like a net force in these situations. Then divided by net mass that you're attached, 30 plus 15. This will give you then 5.0 meters per second squared to the right. Okay, so that's what I'm done step one. We found the net acceleration then, or the acceleration system. Make sense? Okay, two. The acceleration of each object, they are moving in the same acceleration in this case. So both the acceleration of the k, oh, it should be a, sorry. Acceleration of the k would be the acceleration of the j, that is same as the net acceleration applied in this case. That would be 5.0 meters per second squared to the right again too. 3. The net force on each object can be found from this. The force on the k is mass of the k times A of the k. Okay, the k has the 30 kilo. It's have the acceleration of 5, giving you 150 newtons. Okay, I would call like a net of this. Just put the net force on the k. What about the net force on the j? This would be mk, the net of that times the j, I should say. mj times the acceleration of j here again too. That we have given that 15 kilo times 5, they're giving you the 75 newtons for both of them to moving to the right. Guys, please follow that step by step, because you will get to really complicated questions later on. But again, I'm using the same like a method to solve the question. Okay, then after get it over here, question 4, let's find the tension in each strings or the rope. So to find the tension, we need to know what system. So let's have a think about system in the J. J is moving in this system here. It received that tension force moving into this direction, isn't it? Okay, now let us think about what's on the forces applied in here. It has the net force. It has a net force moving into this direction to the right from J. It's 75 newtons to the right, isn't it? Okay, so what can you tell from here? Oh, this is the only force applied on the J is a tension force, and then if the net force is that 75 newtons, can we say this is the same as a tension force then? That's not what you need to do. Okay, draw the force diagram again for individual boxes or individual systems or individuals, and then you can figure out therefore the tension force is 75 newtons on this direction to the right. Does it make sense? Too easy? Okay, next one. What about K? The box K. Box K is receiving some applied force. Okay, it also receives some tension force backward there. So make sure you remember that tension force is kind of in the moving in both directions. So this with the tension force applied. Okay, that would be the applied force of the 25 newtons kind of applied to that K. But the net force, most importantly, net force on the K is given as 150 newtons. You got the idea here? Okay. So can we say that net force in K is the sum of the 225 newtons that's applied forward plus that the minus T like this. Then what about the tension force? Could it be 75 newtons in the case to the left? So just kind of prove that, oh, the tension force in between J and K is the same magnitude with the opposite direction too. So that's working as some sort of the action and reaction force in this case. But that's how you can solve the question. Does it make sense? Okay. All right. Let's have a short, like a 5 minutes break or toilet break, and then we're going to come back to some of the questions, similar questions there, B and C, and we're going to do the vertical forces too. I'll leave that template, leave that kind of method here. Okay, with the same method, could you try for B? That's page 55, and C, please. Question B and C, a little more complicated, but give it a go. Give you about 6 minutes. So that's page 55 and 56. Give you about 6 minutes. This is a huddle for year 11 physics. So people found that this is really difficult to understand. So they get tipped over a lot and drop physics after this chapter too, a lot, understand. But which means if you can get over this hurdles, like no, there should be much problem in the rest of the year 11 physics. Module 3 is quite relatively easy, 4 not much. Remember that we finished almost half of the year 11 contents now. Yeah. Module 2. Whoa, yeah, we finished the half. Nice. Okay. All right, let's have a look at the questions together now. I mean, please watch like what I'm doing. I'm just following the templates provided here again too. It's also given in the 1, 2, 3, 4. But sometimes the question is simply asking you to find the tension force without telling you the step-by-step guideline. This is every single time dealing with this type of questions, with find the tension force, pulley. This is the way. This is the method. Golden rule, you can just remember, screen capture that or just take a photo of that, write it down, print it, have that with you. Okay, this will help you. Now, we have the QRS now attached with the string 1 and 2, and now it's moving at 16 newtons. So, first, imagine that pulling everything at 16 newtons means that they will be moving in the same direction with the same acceleration. It's one thing that you must understand. They're moving with same acceleration. Means that we are able to find the total acceleration by the net force applied divided by net m. In this case, net force will only be at 16 newtons. In this case only, that means we have 4 plus 2 plus 6. Giving you 5 meters per second squared to the left. Okay, Matthew, then what would be the acceleration on Q, which is R, and acceleration of the R, and acceleration on S?
5 meters to the left.
Yeah, they'll be the same, which is 5 meters per second to the left. Very good. Remember that this is the key to solve the question. From here, we're able to find the net force applied on the Q, net force applied onto the R, net force applied onto the S individually. Remember this again, net force means that it's resulting in that motion, with the same velocity, same acceleration here. The way we can find that, I mean, how do you find the FQ?
4 times.
Yeah, so MQ times the AQ, make sure you show the working out, relative working out in here. 4 times the 5, giving you what? 20 newton to the left. Same method, MR times the ARR. Guys, I value that. I do. Write down all the relative working out. Don't just write all the values in. Not a math exam, physics, chemistry, biology. Oh, not biology, physics and chemistry. I value the all the relevant working out. Not only me, all the school teachers and markers will value this too. So make that as your habit. Mass of the S times the acceleration of the XS, that'll be 6 times 530 newtons to the left as well too. Good. Okay. Now, after you've done this over here, let's draw the individual boxes. So shall we start from S? We have box X, S, given here, okay, which is 6 kilo. It has a tension force attached string attachment producing the tension force. This is the only force applied onto S. I can't find any other forces applied in here. So can we say, oh, the net force on S that was given as 30 newtons to the left, but isn't that same as the tension force? Okay, what tension force? On tension force from the string S to the R, or on the string 2? This is it, one answer. Okay, let's do the same thing. We have the box now, R, box R here. It has net force moving into that direction, the left. R is now having 10 Newton to the left. It has the forces that's going up and forward and back. So you're going to see that there's a tension force 1, tension force 2 applied all together. Now, from that S, we do know that, oh, the tension force on the string 2 is 30 Newton to the left. So can we say, oh, T1 is the opposite, the reaction force of tension force would be 30. So this is 30 Newtons, 30 Newton to the right. Does it make sense? Then, using that, the net force on the R is then T2 plus, must say the negative direction, minus T2 plus T1. This is giving you minus 100. Remember that I'm using the negative to show the direction to the left. Okay. Then T1 is giving in as a 30 to plus. So T2 would be what? Moving that 100 minus the 30. Sorry, not 100. So 10. Why keep me saying 100? Handwriting. 10 Newton, 10 plus that 2, they move that, minus, sorry, 10, 30, moving that, minus 30, plus 130 Newtons go like this. Am I right? No, it's actually not. My bad, sorry. Let's go. The net force is minus 10. That is T2 minus T2 plus T1. Therefore, T2 is moving that T1 plus 10, which is 40 Newton. There we go. That means that tension force in T2 is tension on string 1 is the 40 Newtons there. I can do the same method for the next one too, that we have the Q. Okay, you don't have to do a Q, but let's see whether it's true or not, figure out. So we have a 60 Newtons for the 60 Newtons applied, okay? It has a tension force T2 that's applied backwards. Does it make sense at all? Okay, it has a net force of the TQ, the FQ, is given as the 20 Newtons to the left. So the net force on Q can also be found in minus 60 plus T2, that's giving you minus 20 here like this. Then T2, we give the same value, 14 Newtons there. So it'll be the both directions. So T1, final answer, T1 is 30 Newtons the both direction. T2 is 40 Newtons to the both direction. Okay. Am I following the template or like the guideline over here? I tried it too. Okay. I found the net acceleration, then I found the individual acceleration on those, and I found the net force on them. Okay, on the individual like blocks, and then I finally found that the tension force applied. Okay. Try question C by yourself. I give you the answers for question C. For those, string 1, 2, 3, PQRS, PQRT. String 1 would have the 8 Newtons. String 2 would have the 14 Newtons. String 3 would have the 38 Newtons all together. Yep, okay, so that's the answer. Try it, okay? Same method. It'll be exactly same method, like how I did. Like, so I just want to try yourself. And this is the answer. Try it, challenge it, push it until you get it right. You okay, Matthew? Okay, Devin? Not easy. All right, next one. How about this? We have something in the vertical. Vertical. So find the tension in each of strings or the rope by neglecting any frictional forces there. Now, this time you're given, it's slightly different to the previous one. We have a horizontal. This time we have a vertical then. So in the verticals, it doesn't really matter whether you have a vertical or horizontal. I'm going to apply the same rules that applied in here. Okay, so question 4, have a think about here. So it's giving you that the motion of the system, read the question very carefully there, motion of the system upward with the acceleration of 3 meters per second squared. It's giving you that, oh, the net acceleration is giving you 3.0 meters per second squared. It's given upwards. That was given. Yeah, so you don't have to worry about finding the acceleration from here. It's given. Then, can we say, because x, y, and z in the same system, or same box, moving with the same acceleration, then it gives you that acceleration of x would be acceleration of the y, that's the acceleration of z, that would be same as 3.0 meters per second upward too. Am I using the same method? I do. I don't need to find the acceleration, easy, free, but I need to do that over here. Okay, David, up to this point? Okay, what would be the next step? What would be the next step then? Yeah, I can do the find there here. Find the net force on each of the blocks, of the boxes that you have. F on x. Okay, the net force means I can find the mx times the ax. That is 5 times 3, giving you 15 newtons up, isn't it? Same method. F on y would it be 4 times 3. Oh, sorry, I should write it. my times ay, that is 4 times 3, giving you 12 newtons up. Net force on z would be same, mz times az, that would be 3 times 3, giving you 9 newtons up as well too. Too easy up to this point here. I mean, like, no, I can teach this concept to year 7 kids too. They can actually do the calculation there. Okay, but year 11 work start from here then. Okay, then you need to analyze the individual blocks forces applied. So let's draw that again. We have start from the Z, the box Z here. Now, have a consider about the difference between horizontal to the vertical. In the horizontal forces, we did not need to care about the gravitation for the weight force. But in the Z, every single time you deal with the vertical, you need to consider about the mass and the weight. Means that box Z has the mz times g, which is the weight force applied, and it has a tension force applied in T1 over here. Does it make sense? Okay, so for this, net force, however, is given on Z. And what's the net force on Z again? 9 newtons up. So I'll show you that in here. How to find the net force again? Simple. Just find the net force by adding all the force components that you have. Did we do that? We did many times. The T1 plus minus mzg. That's what I'm talking about. Alright, then you know 9 is equals to T1 minus mass of the Z is given at 3 times 9.8. This is giving you that 3 times 9.8, 29.4. So move that. So T1 is find the 9 plus that. 9 plus 3 times 9.8. You get 38.4 newtons up. Is the T1, the tension force in between Z and the Y. Does it make sense? Okay, in this case, in the both direction. Straight away. Shall we do it for the Y then? Now, can you draw the box Y? I'll give you like 30 seconds. Draw box Y. Consider all the forces upon the Y. Show all the relevant forces on Y. Okay, so considering all the forces on the Y, we have the wave force M, Y, and G is pulling it down. At the same time, we have a tension force T1 that's pulling it down too. Okay, these two are the separate forces, so you have to consider that. We also have the T2, which is from the tension force between X and Y there as well too. But all we know about the net force is on the Y is 12 newtons up. So from there, we can find the net force on Y would be adding all the forces that we have, T2 plus minus T1 plus minus M, Y, G here like this. Okay? Now, we found the T1 in the previous box Z. So what we can do, 12 newtons equals to T2 minus 38.4 minus M, Y, and G, which means like a mass of the Y, 4 times 9.8 like that. Then you can easily find the T2 from these calculations. So with 12 plus 38.4 plus 4 times 9.8. 12 plus 38.4 plus 4 times 9.8. You will get 89.6 newtons in both directions then. Yep, does it make sense? Okay. You don't have to go for the X, but if you want to do, like you can check the answer with the X. So shall we do that for X? The box X have some forces applied there too. So we have the tension force. It's not a kind of negligible force or applied a force there. We have some of the forces pushing it down, and the tension force. So T2 is now pushing this one down. We have an MX, G is pushing down. We have the motion of the system upwards too, so the net force applied and going upwards, going up here like that. Okay, in this case, it's applying to the whole system, so 3 times all the forces, so 3 times all the forces that we have, 5, 9, 12, 36 newtons. It'll be 36 newtons going upwards too, but that's something we can find here. The net force that applied in here is known as X is 15 newtons up. Okay, so do the same method. The F on X can be found by adding the 36 minus T2 minus MXG, which is the kilo of the 5 times 9.8. So if you find that, you'd actually get the same answer from the previous one. So you get the T2 is therefore 89.6 newtons in this case too. Just double check. Plus 36. It's actually slightly different. 36. 5 times 4 times 3. 5.3 times 4 times 3. 36 newtons. Yeah. That's giving you 15. Sorry, I missed out of that. Okay, so we can use this method to any of the questions, but just be careful with dealing with some different force components in the vertical motions too. So that's what you can consider for question A. Okay. Now, how about try for question? Can you try for C this time? Okay, I leave that method T